Today we'll be doing the integral from 0 to pi over 2 of the natural log of the sine of x times the natural log of the cosine of x divided by the tangent of x dx. And to start off, we can rewrite this integral as the integral from 0 to pi over 2 of the natural log of the sine of x times the natural log of the cosine of x, and one of our tangents is the cotangent of x dx. And we'll make a substitution. We're gonna let u equal the natural log of the sine of x, but then that means that du equals cotangent x dx, and the bounds of integration u1 will be the natural log of the sine of 0, which is the natural log of 0, which is approaching negative infinity. u2 will be the natural log of the sine of pi over 2, which is the natural log of 1, which is equal to 0. So we're going to have the integral from negative infinity to 0 of u, the natural log of cosine x, and cotangent x dx is du. So we have to find a way to get rid of the x's. So we said that u equals the natural log of the sine of x, but that means that e to the u is equal to sine x, but that also means that e to the 2u is sine squared x, but that also means that 1 minus e to the 2u is 1 minus sine squared x, but we know that's cosine squared x. So this means that the cosine of x is the square root of 1 minus e to the 2u. So using this, we have the integral from negative infinity to 0 of u, the natural log of the square root 1 minus e to the 2u du. But using logarithm rules, we could rewrite this as 1/2 the integral from negative infinity to 0 of u, the natural log of 1 minus e to the 2u du. And from here, we'll use the fact that the natural log of 1 minus e to the 2u can be rewritten as negative the sum from 1 to infinity of e to the 2uk over k. So replacing this in the integrand, we have 1/2 the integral from negative infinity to 0, and then we have u times negative the sum from 1 to infinity of e to the 2uk over k du. And then swapping the sum and integral, we're going to have a negative 1/2 sum from 1 to infinity of 1 over k, and then the integral from negative infinity to 0 of u e 2uk du. And from here, we'll make a substitution. So we're going to let 2uk equal negative v. So this means that 2k du equals negative dv. And solving for du, we have du is negative dv over 2k. And solving for u, we have u equals negative v divided by 2k. And solving for v, we have negative 2uk equals v. So now we can find the bounds of integration. So v1 will be positive infinity, and v2 will be just 0. So now using this, we have negative 1/2 sum from 1 to infinity 1 over k, and then the integral from infinity to 0 of u, but we said that u is negative v over 2k, and then we have a e to the 2uk, but that's negative v, and du, we said it's negative dv over 2k. So I could cancel these negatives, and I use this extra negative to flip the bounds of integration. So we have the sum from 1 to infinity of 1 over k, and the integral from 0 to infinity of v over 2k e to the negative v over 2k dv, and we still have that extra 1/2 that I forgot there. So we have 2 times 2 is 4, times an extra 2 is 8. So we have 1/8, the sum from 1 to infinity, and we have k times k, which is k squared, times an extra k, will be 1 over k cubed, and we have left over the integral from 0 to infinity of v e to negative v dv. But the integral from 0 to infinity of v e to negative v dv is just the gamma function at 2, which is 2 minus 1 factorial, which is 1. So this entire thing is equal to 1. So we're left over with 1/8, the sum from 1 to infinity, 1 over k cubed. We know that the sum from 1 to infinity of 1 over k cubed is just the zeta function at 3. So that means that now we could say that therefore the integral from 0 to pi over 2, the natural log of the sine of x times the natural log of the cosine of x divided by the tangent of x dx is equal to 1 over 8 times zeta 3. And so that is the final result. Thank you very much for watching.